Mm. You can speak to this. Yeah, I guess so. I can also try to use the phone.
Yinglu, Mark, are you the only two of you there? Are there any other people there?
No, there are two other people. Hello? Oh, okay, it's better. No, can you hello? Hello? Cool. Well, there is no. Hello? 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 How's the sound? Mm. Hold on.
Yes.
Yeah.
What?
How's the sound?
What?
Okay. How's the sound?
Good.
Good? Okay, great. Great. And you see the slides, right?
Yes, I see slides.
Okay, great. Great. So I don't know, use the phone. Yeah, of course. Okay. Yeah.
So today I will talk about the policy gradient methods. And this is the outline of today's talk. And I'll go quickly through the introduction and to the Monte Carlo policy gradient. And if we have some time, we'll go through hectocratic policy gradient. And in the last lecture, Mark have introduced the value space approximation. And that is to approximate the value function or action value function with parameters theta. And with this value function approximation, we can generate policy using like epsilon gradient or Boltzmann distribution to generate policy. And today's talk will focus on directly parameterize the policy, and we'll focus on the stochastic policy, that is the pi theta is given the state S and the parameter theta, and what's the probability of the action taken of A. And this is some classification of these two stream of methods. And for value-based methods, the value function is learned, and the policy is not learned, but using something like epsilon greedy to generate the policy. And for policy-based method, there is no value function, but we have to learn the policy directly. And for actocratic, where we simultaneously learn the value function and learn the policy. This is the vein graph, and let's quick go through. And the advantage of the policy-based method, through this lecture, we'll learn something on advantages and disadvantages. And many of the talks will focus on variance reduction things. The policy-based methods will have high variance, and there's some techniques to reduce the variance. And this is the example for why we directly parameterize the stochastic policy. Because for some application or some real things that the only optimal policy is stochastic. For example, for rock, paper, scissors, and any deterministic policy will be easily exploited, and this is obvious. And So our goal in the policy-based reinforcement learning is to optimize some kind of objectives. And this objective is related to the policy pi. And how to measure the quality of a policy, typically we have 3 or more definitions or formulations. The first one is that starting with the state S1, what's the value of this state following the policy pi theta? And this is called J1 theta. That is how we formulate the objective function. And it's typically used in episodic environment. That means the step is finite. And for infinite episodic, infinite horizon problems, we're interested in the average value. That means the d pi theta is the stationary distribution for the Markov chain under the policy pi theta. That means if we run or the Markov decision process run for a long time, the probability we stay at the state S, that is the d pi theta. And for all states S, we take the average according to the stationary distribution and take the expectation of the value function of all states. And that's what we care about in the continuum environment. And the last one is the average reward objective. That means now we focus on immediate rewards. I have to clarify that in this lecture, I will use the notation of rewards instead of cost. So, so any minimization in previous lectures will be maximization in this lecture, and that there's no difference. And so when we the probability we stay on the state S, and under the policy pi theta, we take the action A, and then we get the immediate reward RSA. And this objective is to measure what is the average reward of the Markov decision process under the policy pi theta. So these 3 objectives are all to measure the quality of a policy. And there's a lot of method to directly optimize the policy, gradient free and using the gradient. And the first naive attack is using the finite difference. Finite difference is very easy to it has advantages. That is, even if the policy is not differentiable, we can use the finite difference. But when the parameter dimension is very high, and this method is not very effective. So we want to analytically compute the gradient instead of using some approximations. That's the motivation for Monte Carlo policy gradient. So we will first introduce the stock score function. We assume the policy pi theta is differentiable, and we want to take the gradient, things we want to optimize directly on the policy space. So we want to calculate the gradient of the policy under the parameterization of theta. And with the log likelihood trick, we can directly formulate the score function. And this is the most important part for the following methods. So, is there any questions until now?
So far, no, but you will talk about I mean, actually, do you have a question about the objective value? So the third one, the objective value is
This one.
yeah. So average reward per time steps. So D is the station distribution.
Yes.
And then after station distribution, you look at starting from there is one more step. So it's sort of one step cost, one step reward.
Yes.
But it's assuming starting that step is already start in equilibrium. Just take one more step.
So in practice, how do you compute this distribution?
You don't, right? You do sampling later on, probably.
Yeah,
you don't.
We don't directly compute distribution, but yes, we do sampling, right?
Okay, so is this related to the previous one, the middle one, the cost?
The second one. I think this is a different formulation because, for example, in the first.
You haven't defined. Yeah.
The first one, in the original paper of Rich Sutton, they defined the first objective.
First one is very clear.
Yeah,
that's the finite horizon problem, right?
Yes, yes.
Or maybe the shortest path problem. Yeah, you have to stop somewhere. Okay. Yes. Then second one is time is going to be run. So what the V pi of S? The time going to be running forever?
Yes, that is infinite horizon problem.
Okay, so what's the interpretation of a V pi theta of S?
I think that takes into account the transient behavior, right? Not just the limiting. V pi theta S means starting from S.
Starting from S, yes.
So what the whole sort of a reward will be starting from S if you run it indefinitely. Whereas the third one.
Indefinitely, it will be infinite, right? Cumulative, right?
Right. So it takes into account the starting point, from starting point all the way to the whatever infinite horizon thing. So it takes into account the transient behavior, convergence like behavior from starting point to all the way to the end. Whereas the last one, I think it only takes into account, if assuming everything's stationary, the limiting reward, right?
I think the middle one, V pi of S often equal to infinite, right? Because suppose each step you will earning at least $1. If you got an infinite horizon, going to be infinite amount of money.
There must be some discounting, right?
Yeah, there is the gamma discount.
For that, there must be some discount.
Okay. So that's discounted one. Okay, good.
Yes.
Then move on. Okay, so it's not truly average problem. Okay, average value.
Yes. So for different formulation, the stationary distribution is defined for different ways, and it can be found in the original paper. And we'll.
So that's okay.
Yes.
Go on.
Go on. Okay. So the likelihood ratio, the log likelihood trick is the most important part for the formula for analytically computing the policy gradient. And it's just using the gradient of the log function. And then we will compute the gradient using the expectation. And I will I will exemplify the intuition behind the score function. So let us consider the softmax policy. That means the probability of action is proportional to the exponential weight. And here we consider the linear combination of the feature, state action feature. And the score function will simply compute it to the phi SA, that is the feature, minus the expected feature. That means how much better is taking action A than the average. So the score function, the intuition behind the score function is actually how much we can gain from taking the action A. And then another example is for the Gaussian policy. That is, the policy is for is sampled from the Gaussian distribution, and the mean is the mu s. That is the phi s times the theta. That is that is how we approximate the state. And the score function will be computed to A minus the average mean times the feature of S and divided by and rescaled by the variance.
Okay,
And
this is not good. Okay, in rules, it's not working well. So,
okay.
So what is the problem now? So the you didn't talk about model now, right? So you are okay. So you just define a policy, and
Yeah.
the underlying problem is you didn't even talk about the underlying problem. That's just just action space continues, right?
Yes, yes.
Okay, so you need to take action continuously in real value. Take action.
Yes, this is continuous action space. And
okay.
I just use this example to exemplify the intuition behind the score function, and that is the how much better we take action A than the average. And then let us.
Okay. Okay. Don't move forward. Okay. Don't move forward. Okay. You're rushing. We need to understand this. Okay.
Okay.
So we need to understand that. So so let's see. The policy is randomized. So taking the action, taking the randomized, taking the uniformly draw from there, right?
Yes.
Okay, and then the theta is there, and so the A has density, so it's normal density, and from the normal density you can take a log and take gradient. Okay, good. That's all right. Good.
Yes.
That's nothing to do.
I think
with
there's a lot of skips. A lot of even the previous slides I have trouble following.
Yeah. Where did you get this value coming from? The second one.
The first or second one?
The expect value, the last line.
Yeah. How do you get the score function? You say, well, this is natural, intuitive.
You can compute the softmax. I mean, if
softmax is the one that on the display on the right. That's softmax.
No, that's proportional to exponential weight. So it will divide it by the summation of all action.
Okay, I see. Yeah. So that expect value is coming from the summation.
Yes.
Okay.
If you carefully calculate it, yes. You take the log and there will be the minus, and then you take the derivative, and it will be the probability comes taken out. So it will be the expectation.
So you should display the actual derivation, even though it's just maybe a couple of lines.
Right. If the entire slide is making pronunciation, making claim, that's a problem, right? That's a problem. Some you can say some will be not doing details, but somewhere you need to do details. Yeah.
Okay.
But now this explanation better. Now I see why the second term is value shows up. Yeah.
So, is there any questions here? Okay. So, and about the second one. Okay, I'll continue. So before going to the multi-step episode, let us first consider the one-step MDP, and also called the contextual bandit. And we'll start from the state S, that is follow the distribution of the starting state distribution DS. And our objective is we're using the third objective, since we only have one step, and the second and the third one is actually the same, equivalent in this situation, and the episode will be terminated after one time step with the reward sample from the RS and following the policy pi theta, and will take the action A. And this is the example for calculating the policy gradient using the score function for one-step MDPs. So the excitation here is on both the state and action under the policy pi theta.
Is I thought D will depend on pi as well, right?
Because it is one-step MDP, so so we only take the initial distribution, and I think initial distribution is not depend on the pi.
What does that mean? This is not no context. It's not interesting problem, right?
I just give an example for calculating the policy gradient using the score function, and I will go next. I will go to the our usually multi-step MDPs.
Okay, so let's look at your case. Okay, the score function. So the gradient of pi is equal to the score function. Okay, and okay, so that because that's the one. Okay, so you just take gradient of pi, and that's using the formula, right? It's already on the previous slide. The pi times the gradient of log. Is that right?
Yes.
Is the gradient of pi is equal to the pi and a gradient for say, can you go back to the previous slide? So did I miss something? The formula for the grade?
This one?
Oh yes, that's one, okay? So the likelihood ratio, okay? Good, perfect.
Yes.
Okay, go back. Go forward.
Okay. So
last slide, no. Let's look at the file the XP value. Let's see what's going on, XP value. So it's averaging over S, averaging over A. Am I right?
Yes. Both there's randomness on the state and also on action.
Okay.
And, yes, but the initial distribution is also under the it's not under the policy. Is
that notation is the problem, right? You have used e pi already, pi theta before.
yes.
Or maybe it's okay. That's the first expression. First expression, you're also using pi theta, okay? E pi theta. It's a bit strange. Okay, go on.
So for multi-step MDPs, the intuition here is to replace the immediate reward R for long-term value, the state action value, that is the Q function. And there is this is exactly the policy gradient theorem. And how do you say? We're not going to the proof, and the proof is not very hard. And we'll say that and here we just replace in the previous slides, the immediate reward R because here we are facing the multi-step MDP, so we have the accumulated reward, and the accumulated rewards starting at S and taking action A and following the policy pi is actually the Q function under the policy pi of S and A. So we will have the policy gradient that is similar to
I don't understand that first line.
first line.
You're correctly.
The first line is
why there's no derivative with the Q? Why there's no derivative with respect to D?
I didn't write the proof in these slides. How do you say? So the objective is actually, for example, we use the first objective, that is the accumulated rewards starting at S1 and following the policy pi theta, and we take the gradient on the objective. We will have we will have two terms, and in the second term we will sorry, I'm not going to talk about the proof because I just want to compare the one step and the multi-step, and
okay, I think okay, this is my speculation. I think that you're using that D is the distribution. So summation of D, likely summation of D equal to 1. And that gradient of that one is equal to 0. So maybe that term somehow will disappear, somehow there. And then for the Q term, how does it disappear? Q term, again, maybe, yeah. I'm not sure, okay? So that the Q term. Then you have the same thing. Then what is that? What's the last line? Okay, the last line you're adding gradient equal to pi times score function, right?
Yes.
Pi times the score function. And so therefore expect value of that. Okay. Yeah. So the last line is using that definition, that score function.
Yes.
Okay. Now this is for the other people. I'm not sure who will do the. The other is Yuan on the line online. Other people will follow, right? Will do the future presentations. I think it's this you need to do some proofs. Okay, this kind of seminar.
I have some proof in the. I have two proof in the lecture, and yes.
Okay. Okay. Go on.
But this seems to be an important theorem, right? So would it be nice to see some simple argument for this or intuition behind it?
So the intuition here is actually transferred from one step to the multi-step, and the actual derivative is actually not very hard. It's just 4 to 5 lines, and
I know it's not hard, but one step and basically D and R are not dependent on theta.
Hi.
Right?
Yes, yes.
That's the important difference.
See, Yinglu, you're already wasting a lot of people's time because you skip something, right?
Yes.
You're waiting. Go on.
Okay. So using the policy gradient theorem, we can use the sampled unbiased sample of the Q pi theta. That is actually when we sample a trajectory or an episode from under the policy pi theta with the Markov decision process, we can have the accumulated return Vt starting from the time step t, and that is the score function and times the accumulated return, and we will update. Here we'll do the gradient ascent, so we'll update the parameter theta using this unbiased sample, and this is actually the this is directly following the policy gradient theorem. So for each episode that is sampled from the under the policy pi theta, we will update the parameter theta for each state action pair, and for each state action pair, we have the this unbiased sample of the Q function. That is Vt. So that is in the algorithm in the fourth line. So this is the Valina or the classical policy gradient method. So any questions in these slides?
So the episode need to run to the end, right?
Yes, this is finite, right?
So the episode has to be running toward the end. Then you can going backward to at the time t, you get the cost to go function Vt, right?
Yes.
Okay. Yes.
Or reward go the same.
So this is using one episode and update theta capital T time.
Yes, for one episode, we update because there is a T-1 state action pairs. So each one can be thought as the starting point.
Right. So you said this is reinforced algorithm. This is this going to be now the next one is going to be repeat different theta, right? In step 7, now you're going to using the new theta to generate another episode. Is this right or what?
Yes, we will have one episode and we update for T-1 times and we generate another episode.
So this is what it means, 7, line 7, return theta, maybe do it again, right?
Return theta is for generate many episodes, then we return the theta.
Say that again.
What?
Say that again. I think this one is for each theta, given theta, you do the one generate one episode, right? That's in line 2.
Yeah, so I guess in the second line, like there is like for each episode. So we generate one episode update, like for in during this episode we update.
So there's another for loop, right? Basically, for all episodes, and then there's another end for.
Yeah, then we use another episode.
Yes.
So what is this capital T? Can you explain again?
The capital T is the horizon of the episode. That means our episode must it's not infinite, because if it is infinite, we will the Monte Carlo method we will not get exactly the return, the exact return.
Mm-hmm. Or even if it's infinite, so you terminate after a little bit, right? After some time.
Yes.
So what I'm saying that is this algorithm here, algorithm 1 is that this now you need to see the loop. Okay, there's 4. Let's see.
The first loop is for each
Episodes.
and the second loop is for every state action pair.
So how many episodes for that theta? For one theta, you can do multiple episodes or what?
Yes, multiple. The initialization of theta is just for once, and then we sample many trajectory or many episodes. And for each episode, we have T state action pairs that is to update the theta.
So when I generate second episode, do I use the original theta in initial state in line 1, or I already updated?
We follow the updated theta.
You sure?
Yes, yes. This is because is this any questions or?
That's a question actually. You sure, right? You sure that
sure the initialization is just for one.
So initialization once, but the 7 will be returned back to the change the initialization, right?
Yes, when you go to the second episode, the initialized theta is the one you updated for the first episode.
Okay, that's fine. What about 7? 7, you ending there? Just 7, that's the last theta, is that right? That's the final theta, return 7?
Yes, that's the final theta. For after update for example, for n episodes, and then we return the final theta.
Okay. Okay. So the policy iteration is happening at line 2. Right? Policy iteration. So you given one theta fixed, that's one policy. So for that policy, you just generate one episode. And then when you change it to new theta, the next one you're coming back to using new theta to generate another episode. Right? Each theta generates just one episode. Am I right?
Yeah. So this is ambiguous. So
right, this will have a lot of problem. I think certainly that's not AlphaGo 0 doing. But go on.
So I didn't quite catch it. So what is ambiguous?
Ambiguous here is that so for one theta, do we sample just one episode or multiple episodes? So actually, in practice, both are okay. So it depends on the problem, I think.
I think this is something there will be a lot of my feeling is that there's a lot of fluctuation going on.
So,
If sample
yeah, my gut feeling is there should be some averaging for theta. If you run one episode, do this, you initialize from the previous finished theta and continue with another new episode.
Yes, this is
That strategy that's what you said. This what this algorithm is doing. But to me, each different episode generates different theta. There should be some kind of averaging on these resulting thetas to get rid of the variation of each different episodes. No.
But I think let's leave this thing here. I think you will not be able to give a precise answer here. So leave it here. Just keep sharp mind. This question will coming back again and again. Okay.
One question about the third and fourth step.
Pardon?
One question about the third and fourth step. In the third step, so we can update the theta minus 1 time, and in the fourth step, in the right-hand side, we have two theta. One theta minus alpha about the gradient about the log pi. But in the gradient of the log pi theta, the theta is always the initial theta. I mean the theta in the episode. So it's two things in the right hand side.
The theta will be updated. So actually, for each state action pair, once you update the theta, and the next time you compute the these policy gradient, you will use the new theta.
You mean in the first step, in the pi theta will change.
When you update the theta, the pi theta must change because the policy is parameterized on the theta. So when the parameter changes, the probability to generate the action will be changed.
I mean, when we update one episode theta, we can do t minus 1 times, right? But when we take the gradient in the fourth step, the pi theta should be the theta we generate episode.
So actually, for each episode, the pi theta will be the same for each episode, because that is how you generate the episode.
Yeah. So in the first step, the gradient about the log pi theta, the theta won't change in the t minus 1 times.
So you are talking about some fitted iteration problems. So I think this is a general form of the reinforced algorithm.
Oh, I see. I missed that. So that's a good point. So the episodes, different episodes are not generated all at once. So for the first episode is generated from the first theta. After this loop, inner loop, you get a new theta, new policy, and then you generate a new episode according to this new policy.
Yes.
And keep iterating. That makes
exactly.
Exactly.
That's each policy just generates one episode. That's what.
That's right. Yeah. So then
what I claim is that's not the case for AlphaGo 0. So that's but there's a lot of variation here. So let's take that literally what he's doing. That there's no point to beating him further on this.
Right. Yeah. Okay.
AlphaGo, I think they're not using policy fit method.
What?
AlphaGo is
but
not.
We get that later. Later, AlphaGo 0. Don't get into that. But
okay.
something.
Well,
that's maybe distraction.
Okay.
I have a question.
Well, okay.
The first is how to choose the learning rate alpha, and the second is how many episodes will you generate for line 2? I mean, what's your stopping criteria for this reinforcement?
This is a good question, but it depends on the problem, and actually for the learning rates or the step size, and you can use any kind of optimization, first order optimization method, including some like they're using the conjugate gradient or something, and also in this algorithm, I just put out the general form of the reinforce. That is to use the score function to update the theta, and combined with the cumulative rewards. That is V, the reward to go function. So let us continue. And we'll see here that the using the sample will take us high variance. So the next part will talk about how to reduce the variance. There is a stream of method that called active-critic, and things in the reinforced algorithm 1. We always use this unbiased sample of the Q function, and they will contain high variance. So in this method, the intuition here is to estimate the Q function under the policy pi theta using another parameter, and so it will bring us two set of parameters. The first is still the theta, that is for the policy, and another set of parameters, W, that is for estimation of the Q function under the policy. So once we have the fairly good estimation of the Q function, we will not always to take the sample that will have high variance. So this is the motivation to use the critic. And the active critic actually is combined, is a combination of the policy-based method with the value-based method. And if we have good estimation of a Q function, that is the QW, the parameterized on W, we can replace the original exact Q with the approximate Q, and we can get the approximate policy gradient. And
maybe the last
typo? Oh, the pi theta. The theta is should be the subscript. Yeah. This is typo. So the problem is how to estimate the Q function fairly good. So this is the critic solving the similar problem that is in the previous lectures for policy evaluation. And for policy evaluation, in Mark's lecture, he talked about the Monte Carlo policy evaluation and TD0 and TDN, and also the TD lambda. So all these methods can be used to estimate the critic. So let us assume the linear value function approximation for the critic. That is using the feature of state action feature times the parameter W. And for actor, we still use policy gradient to update the actor parameter theta. However, we instead we use linear TD0 to estimate the value, the state action value under the policy pi theta. And different from the algorithm 1, we don't use always use the sample sample reward to go. However, we use the reward to first estimate the critic, that is QW, and the delta is actually the one-step TD arrow. And so in this algorithm, we initialize the state and theta, and we also sample the action from the current policy pi theta. And for each step, and this is online algorithm. So for each step, we first sample the reward following the state and action we just sampled, and also for following the MDP, we have the next state, and following the policy theta, we have the next action, and for we're using the TD0 to compute the TD, that is temporal difference arrow, and if we following the linear least square policy evaluation, we can directly take the derivative. We will have this in the line 6. That is to update the Q value function with function approximation. And in the 5th line, that is just using the estimated Q function to teach the actor to say which way will go. So this is in the 2th part, the separate part. The first part is to use a value-based method to estimate the Q, and the second part is use policy gradient to update the actor.
What's a line 4? Line 4 is for what?
Line 4 is just the TD0.
Yeah, TD0, is that complete? So that QW updated or what?
Pardon?
So the delta is used for what? There's something missing, right?
Delta
used
in the
6.
Yes, that is for least square policy evaluation.
Oh.
Yes.
Okay.
So we have the target. We have the target Q value, that is the immediate reward R plus the next state action value Q, and then this is similar to temporal difference learning.
Yeah, exactly, temporal difference.
So basically, 4 and 6 should be combined, right? Delta is the intermediate value you're evaluating.
Well, he doesn't want the W to be updated before 5.
Then delta can be moved to after 5, right?
Can delta be moved to 5?
4 and 6 are together.
4 and
me.
6 together. Yeah.
5 is sort of independent by itself.
Yes, but the delta compute in 4 or 5 will not affect other part.
To me, delta is an intermediate value. It's a sort of a stochastic sample of the expected value of the TD0 approach, right?
Yes.
Yeah.
Of the,
So you have 2 updates, right? You have 2 updates there. One update theta,
is-
policy update.
the other is
Policy
W.
Yeah, then the W update. And
Delta is the intermediate value. Or you
the
can
4
just
should,
combine.
line 4 should be moved down. Mhm.
Yeah, 4 can be lumped into 6 altogether, actually.
Yeah.
I was going to ask, where's the step size for the TD0? And I couldn't find it in delta. I thought delta is the complete sort of a TD0. And then I was going to ask, where's the step size?
Step size beta.
Beta, yeah. So then in line 6, I found beta. So delta should be substituted into line 6.
We can directly write the TD arrow into the 6.
That's right.
Yes.
Yeah. Just
Exactly.
substitute delta into line 6, and then you're done. Basically.
Yes. Yes. That's more convenient. And so this is 2 parts. So any other questions?
I just want to make one comment. Is again, I bring up AlphaGo 0. AlphaGo 0 is these 2 network W and W Q approximation and pi approximation using the same network. So it's a high dimension W and theta.
Yes, double DQ and things
What?
like that.
What's your question? What's your comment?
Oh, are you talking about two set of parameters that is for the same Q or some?
Certainly they're using same step size. So it's a one network output both Q and pi. One neural network output both Q and pi.
Yes. That's dueling structure. Dueling double DQN.
Oh, are you going to talk about that? Okay.
Yeah. No. I'm not going to talk about this in this lecture because that is the.
Okay.
Yeah.
Go on.
Go on. And things the Q value function is approximate, so there must be bias. However, we reduce the variance, so there is bias, variance, and trade-off. And for the next theorem, the compatible function approximation theorem tells us if we carefully choose.
Is it possible to give some insight why using this W or this approximate value Q value function reduces the variance? What's the intuition there?
The intuition here is that so in the first algorithm 1, we always use the sampled episode and using the reward to go sample, and for each sample there is high variance for each sample. But here we use the estimated Q function instead of the sample, and things the estimated Q will not change that fast. So according to the algorithm, so here it will give some like how do you say? So it will give some stable, much more stable than the just sample from
So let me help a bit, okay? So let me help a bit. You go back to the previous line that was the VT. Where's VT?
VT. Oh,
Yeah. So the previously the VT. How do you compute VT? VT is from RT, R small t plus R t plus 1 plus
yes.
R all the way to R capital T.
Yes.
And each one is random. So that's a lot of these many random terms adding up. All right. So very noisy. And what he's doing in Q is using the Bellman equation. So you think of cost-to-go function VT is going to be, if you have a previous t plus 1 is already being estimated, right? VT plus 1 here is already being estimated. You just need to sample one of them, RT, R small t, plus something already be sampled. And by doing this, using Bellman equation, you reduce the variance tremendously, estimate.
I see. So essentially, you have this QW on the side, which takes into account the history of the rewards, of state action pairs and so on, and the associated rewards, and that is better than just looking forward, right?
Right.
Just look at the VT value is just looking forward, but this QW actually accumulates all the history that you have visited so far. Okay, makes sense.
Yes. So, and they in practical they have some experience replay buffer, things like that, and we will focus on not too far away history, but more recent history. And so, any question about this page?
Yeah, can I ask a question? So here you consider discount from previously in first album you consider horizon
because here it is the so you can see if that is for each step. So for TD we only look ahead for one step. So it can be used in the infinite horizon problem.
So policy gradient theorem is valid for both kind of objective functions.
Yes.
Okay.
Yes. Okay. So we were talking about the bias and how do you choose a good approximator. So the compatible function approximation theorem tells us about if the function approximator of the Q is compatible to the policy, that means we take the gradient on W of the QW will be equal to the policy gradient. And the second condition is that a value function parameter will minimize the mean square error that on the expectation. Then the policy gradient will be equal to using the another parameter W, and the proof is here. Because
before you talk about proof, let's see understand what does it mean. Okay, so let's see. So okay, so exact meaning, okay, that's equal to space value. Okay, so previously the Q, you need an actual Q, right?
Yes.
If you actual Q always exact. Now using QW is the approximation of the actual Q, right?
Yes.
And but you claim this one is still true, right? This the space value is still true, right?
Yes.
And in order for this particular version of approximation, you need what? You need
So it
Unique.
actually tells us about the first condition is that for you're taking the gradient on different set
Yes,
of.
I understand. I understand. We don't need to repeat that. So that you need to must first satisfy the first display. Okay, the choice of QW. So think of for pi is already given or something. So first one, QW satisfied. Then second thing, the choice of W has to satisfy. The second one has to minimize that.
This is actually equivalent to for any state action pair. The approximator will actually be the how to say. So it will minimize this Bellman error. Actually, this
is not Bellman error. I mean, you need to require the choice of W is within that family function need to be minimized that in L2 norm minimized. Okay.
yes.
L2. Okay. And there. Okay. Now you providing proof. Okay. Go ahead.
So the proof is it's just when you minimize the mean square error, take the gradient, and actually take the gradient and following the score the first condition and the 2 to the 3 and you take and that is very direct proof. And for the last line is actually the gradient of the policy gradient. Oh, there's also a typo here. Sorry, the pi theta.
Okay, good. Yeah, I can see the proof.
So then I will introduce another method to reduce the variance. That is the baseline.
So the previous line, you reduce a bias, right? You should basically reduce a zero bias.
Yes.
Okay. And you introduce Q to reduce the variance, but also this particular choice is also reduced, becomes zero bias. Okay.
Yeah, about the compatible function approximation theory, I think the first condition is very hard to satisfy.
Oh, this is so that means once you satisfy this condition, you can have this.
So how to
but actually in practice, there always be bias here. So this is the way that you minimize the bias to zero bias. But in practice, there's always introduced bias when you use the quadratic. So next I'll talk about the baseline. The baseline here is actually if you take the so we want to reduce the variance, but without changing the expectation of the function. So we want to use the baseline. Baseline function is only depend on the state. So when we plug in the baseline function into the score function and take the expectation, we will have the zero mean. So because we can take out the baseline function out of the inner summation, and then the the summation over pi theta for all action A, it is actually the constant 1. And you take the gradient to the constant, it's actually the 0. So the expectation of the score function times the baseline function is actually 0. So for any baseline function, if you subtract the baseline function from the Q, the expectation will not change. However, the variance will be changed because we will take the variance of the subject the Q subject then bias. You will get the you will take the, so you can calculate the variance, and then if the variance so you subtract the baseline. For example, if the Q function of some state and action is 99, and that means you have a good action, but for bad action it is 97. However, you cannot differentiate which is bad or good. When you subtract a baseline, for example, the 98, and the first action, state action pair will be 1, and the second one will be -1. And then you will have, you will easily to differentiate. So we can go gradient ascent to the good action and gradient descent to the bad action. So that's the intuition behind using the baseline. And a natural baseline is that is depend on state. That is the value function. The value function is only depend on state. So when you rewrite the policy gradient using the function Q minus the function V, that is called the advantage function. That means what is how much better you take action than the average. That is advantage. So in the last line, you're taking expectation on the score function times Q is exactly the same with production with advantage function, because the baseline's expectation is exactly 0. So here we will have another question: how do you estimate the advantage function? The advantage function here, we can use 2 parameter or 2 critic to estimate the advantage. You use V to approximate the V value, and W to approximate the Q, and then we will approximate the advantage function. And this is very naive approach because you introduce more parameters and then we introduce more noise. We can see that we can use TD0 to estimate advantage function only using one set of parameters, that is for V. Because so we can see that under the policy pi theta, the reward plus that is reward to go, and this is a temporal difference TD0 arrow. And if we take expectation condition on the state and action SA, we will immediately get the the advantage function. So this tells us that the TD arrow is actually unbiased sample of the advantage function A. So we can use the TD arrow to compute the policy gradient. So any questions here?
So I still don't quite understand the intuition why using baseline function will help reduce the variance further.
So for example,
I mean, this slide, okay, just showing the gradient is 0 if you use baseline function here. But this doesn't, I mean, it says it's legitimate to subtract the baseline function from the actual QW function, right?
yes. So when you calculate the variance for Q minus V, and you'll get.
It only says it's not going to hurt. In the worst case, you can choose baseline function to be 0, right?
Yes, and
But why does it help?
If you calculate the variance of the advantage, you'll find that in the first term, that is expectation of A squared minus the expectation of A, the square of expectation of A. And the expectation of A is exactly the same as expectation of Q. But for the first term, you subtract a positive value that is less than Q. So you will have lower variance if you subtract to the value function.
Okay, there's a bit of an argument. I mean, it would have been nice to show that.
Yes, actually the optimal baseline is not the value. If you take the gradient, you will find that the optimal baseline is actually related to the log pi. And yes, I didn't show this here. I should show this here. And another intuition here is that if you have fairly large Q value, and for example, you take a wrong action, but also gives high Q value, but it is relative more than a good action. For example, it is 50 if you take the wrong action, and if you take the good action is 1,000 or 100. It will in both cases the gradient, if you take the policy gradient, it will go ascend direction. So it will not differentiate what is good action or what is not bad action. So if you subtract the average function, that is the value function, and you will get the 25 if you take good action, and minus 25 if you get take a bad action. So this will differentiate what is good and what is bad. That's another intuition here. And
your explanation is I think that right. If we just using, if you go to previous slides, if you're just using the Q to help make decisions, right? Yes. Using like a Boltzmann type of argument, like softmax to do that, then your argument is correct. Okay, that's the intuition is correct. But here it must be coming from that red one. But using this one version must be when you do the sampling to give you somehow reduce the variance,
Yes,
something
yes.
smaller variance. That must be coming from there. So the your say function value is closer. I think that right. The first one, if you're just using A or Q to directly make decisions using softmax, then your argument is correct.
Mm-hmm.
It's easy. Okay, good. Go on. I think it's yeah. This need more more time or something to revisit.
More details,
this.
I think.
Yeah.
Yes. So next, I'll continue here, and we just talk about the TD0 arrow is actually the unbiased sample of the advantage function. So so for policy gradient, we replace the V reward to go VT here using the temporal difference, and this is actually the same when you take in the expectation. And if we use the approximate value, and then we will have approximate TD arrow, and this is not unbiased, but however it will also like the other quadratic method will reduce the variance. So any questions about these slides?
What's the algorithm? The algorithm, you need to update 3 parameters: V, theta,
No.
and W. Am I right?
No, the 3 parameter is here. That is not good. So we use the temporal difference to just use the V parameter instead of
V and Q are together basically. Right? V and Q is the same thing, right? So if you want to use one network, if you approximate Q, you compute V directly, or you compute V, you can compute Q directly. Is that essentially that's the idea, right?
That's the idea. Yes.
Okay.
And using the fact that the TD arrow is the unbiased sample of the advantage function. Okay.
This is almost like the distraction. Okay. Yeah. Okay.
So for the last few sets, it's actually the same as the Marx talks, and that is how do you do policy policy variation. So we have so for the TD infinity, that is the Monte Carlo. So we use the reward to go function sample VT, and for TD0 we use the TD target, and this is actually the TD arrow in total. And for TD lambda, that is spent from TD0 to TD n, and that is the lambda return. So these methods are all used to estimate the value function.
Value function which is used in the it's called baseline one, right?
What do you mean by baseline?
Baseline function or something. You use you said this all method is using TD lambda or TD. These are all used for the purpose of doing value
evaluation.
And the reason V is used, you actually try to estimate a Q through the V as well, right? So
yes.
Remember
so now
earlier,
focus on the value function, because if we have the value function, we can have the advantage function, and we don't care on Q right now because we yes.
Okay, so basically yes, that's good message. So instead of using Q, so once you have value function, you have advantage function. Okay, good.
Yes.
And part we're not, if we didn't understand the early version of the TD lambda or something, it's very difficult to explain.
Yes, so it follows from the Mark's lecture.
Okay.
Yes.
For the backward view TD lambda, I think the gamma is a discounting factor for reward, and lambda is a discounting reward for eligibility. But for you to get update ET, I think we don't have to times.
Which
Yeah.
one? You mean the ET, the second line?
Yeah.
What's your point?
I mean, we don't have to. Why do you times the gamma? I think gamma is enough. Gamma is a discounting factor for
Factor, right? Gamma. I thought gamma is the discounting factor here.
Yes, gamma is discounting factor.
Can you go back and revisit this Q and V business and A, their relationship? I was a little confused.
Is this page?
Yeah, so this is Q, V, and
Maybe this page.
yeah.
And this,
So previously you were using actor critic algorithm, you use QW and then updating W and updating theta, right?
yes.
Right now you use, instead of QW, you're going to use
V.
V function or A function or advantage function.
Yes, we use V function.
Actually, you want to use advantage function, right?
Yeah, our final we want to use advantage, but we can find the relationship between the value function and the advantage function.
Right. Value function is basically the baseline function that you talked about.
Yes.
Try to reduce further the variance when using QW.
And this is when you are using two function approximation, there is more. We will introduce more noise here. So instead of doing this, we apply the fact that the TD arrow is actually the unbiased estimate of the advantage function. So here, from now on, we can only we only need to estimate the V function.
So what do you update now? So you update theta for sure, right? And then you update the
V.
value function, V?
Value.
Now, when you update theta, don't you need QW? You don't? Or A function?
Right now, we don't need to Q because the expectation here is the same as previous. We replace the Q with the A, and the A is related to only related to the V right now. So we only need to estimate V and use it to update the policy gradient.
Oh, I see. Delta pi theta, this guy. Expected value is exact. I see. This second bullet is very important.
Yes. This unbiased estimation of the advantage function.
I see. Then you don't need to keep track of QW.
Yes.
So Q
Exactly.
function anymore. Cool. Okay.
Yes, so from now on, we need the credit becomes the value function b, and so we need to estimate the value function. So these are all the methods to estimate the value function. And so once we estimated the value function, we can use it to update our theta. That is, there's two variants. First one is the Monte Carlo policy gradient. That is to see the complete return, and use this return to minus the average return from current state. That is the advantage function. And the last line is actually the is the same for advantage function, because we use the relationship between TD arrow and the advantage. However, this will exactly introduce bias here. Oh, you are right. There is no, actually, there's typo in the previous page. There's no gamma in the eligibility traces second update. And if we have so here we consider the linear approximation, and so the point of this page is actually the to substitute the feature. Sorry, I think this page should there's something missing here. No, okay. So this is actually the linear approximation. So the value function here is the phi theta times the times b actually. So we substitute the phi theta to the gradient, the score function, the gradient of the score function. And that is the same as using the backward view of TD lambda. So just replace the feature function to the grad log pi.
I think you're losing a lot of people at this point. This is too much and then too little detail, too little explanation.
This page,
I don't know what you're talking about right now. So you're just flipping back and forth. Well, what point are you trying to make now?
Oh, I want to make point that on the backward view of TD lambda, that is to estimate the value function. And this is the detail on the backward view TD lambda estimation on value function.
I know it's difficult to follow at this point.
Okay, well, we can skip this page for this is not the most important things. And here, here is there's another example for it's actually very similar to the second order method. The picture here we want to show is that when we do parameterization on the policy, we need to find a good direction for gradient. However, for the probability space, the parameter, sorry, a good parameterization is very important. And if you initialize not very well, and the sampled trajectory or sampled episode from under the policy, we will be sensitive to which method or which kind of, how many parameters you parameterize the policy. So for example, in the picture, the axis is this is example for the robot controller, and you have these immediate gain theta 1, and this is the exploration gain theta 2 in is equal to sigma, and you want to have so if you want to converge to the -1 point. So, however, this parameterization is not very good for how to say, for the first.
Hello? What are you doing?
Hello?
So what is so-called natural policy gradient? You didn't explain?
Oh, I didn't. I'm talking about the motivation here. And the natural policy gradient is actually is to estimate the second order information using the score function. And it's very similar to Newton method. However, it used the score function to take the expectation to estimate. It's actually to estimate the second order information in these gradients. And actually, we scale the gradient on each direction.
So why is it called natural policy gradient, and why is it parameterization independent now?
Oh, natural policy gradients. I don't know why they call it natural policy. And
why is it independent of parameterization?
So actually they so if you think about the how do you explain the policy? The policy is actually the is a random variable, and and how much from the parameter can tell about the random variable can be estimated from the score function, that is the likelihood ratio. And if the policy is can be effectively expressed by the so there is some direction that is cannot or some parameter that cannot tell much about the policy you approximate, and some will tell much about the policy. So if we rescale the policy by these kind of second order information, we can have better gradient descent or gradient direction.
Okay, so there's not much point to further discuss this. Let's move on.
Okay. So this is the derivation of the how to use these how to derive this natural policy gradient. That is, if we have the compatible function approximation condition, and we can take the excitation over the advantage function, and the advantage function we take the integral on the on the first, this is following the compatible function approximation, and we can directly get the gradient of respect to the theta, that is the Fisher information times the W. And in this formula, we can know that we can update the actor parameter in the direction of quadratic parameters. And I think that's why they call it parameter independent. And because
I don't understand these lines. So how do you go from in the middle bullet, the second step? How do you get that?
the second step,
Yeah.
this I think we can go back to the compatible function approximation theory.
No, compatible. You already wrote down the first bullet.
That's the first condition.
Yeah, the two gradients are the same.
Yes.
Now, how do you use that to get the second step of the second bullet?
That is, if the two gradient is the same, and you can and the AW is there is no bias when for estimating the true advantage function. So we'll take the integral for the first equation respect to w, and we'll get the advantage function equals to grad log pi times w.
So the derivation is just for linear.
No. This is not about linear or nonlinear approximation. That means if we have the we satisfy the compatible function approximation conditions, we can say that the function approximator of advantage function is exactly this the same as the true advantage function. That is how compatible function approximator theorem says.
Yes, suppose this is not just for linear approximation and we still satisfy the compatible condition. Then we have the first condition, and how we go to the second line in the gradient. It shows AWH to the gradient times W.
What do you mean by if we have not linear approximation?
To derive the gradient of J theta, and in the second equation, we have AWSA equals to the gradient of log I theta times W, right?
Yes.
So if it is not linear approximation, how can we get it? The compatible condition can give us this curve.
No, we are not using the grad log pi to approximate A.
So the compatible function approximation, it's kind of a, so how should we understand this? So the right-hand side, you're saying is independent of W. So when you do the integral, you get a linear function of W.
Yes.
Now, how should we understand this compatibility function approximation? I thought theta and W both are changing, and at every iteration, you want to move in the same direction as if you are using the true pi function, right?
Mm-hmm.
So theta and W, they're sort of related. They're moving in the same. It's not constant, in other words.
Mm.
The right-hand side is not a constant vector.
But it is not dependent on W.
I guess the point is that if you have chosen the parameterization for your policy, then basically, and you agree that your parameterization for a value function is linear, then basically taking the gradient of your parameter, like of your policy, you basically can define future vectors or future functions for your value function on the left side. And then you have a linear approximation of the value function or the advantage function based on the parameterization of the policy.
So you mean must?
No, I mean that if you, okay, so you have chosen the parameterization for pi. So in this way, you know what is the gradient of log pi theta. So basically, this is your future function for the advantage function.
The point is that because we use the linear approximation.
Yeah, I mean, basically, you have proved when you integrate it, you have proved that if you want to have a compatible function approximation, you need to choose linear architecture for the value function.
So I'm not sure this is the right way to understand the compatibility function approximation. My understanding was basically this theta is a function of W. I mean, they're related. They're moving. And every is like two functions. They're the gradient being the same. They're not saying one should be linear of the other or whatever.
Shall we go back to compatible function approximation? Or
Yeah, you can, but I'm not sure we're gaining much more insight or understanding of the situation.
okay.
You think by going back, we will get more information? I think we need better explanation, better understanding of the situation, what's going on.
So I think for natural policy gradient, I don't have enough understanding. And this is actually the last page of this is the summary. And this is the last page. And for summary, this is for the several methods I just talked about. And the first one is reinforce. That is simply use the sampled accumulate return. And the active credit is to use the estimated Q function. And the advantage active credit is to use the estimated advantage function. And the TD is using the relationship between the TD arrow and the advantage function. And D lambda is another point to estimate the advantage function. And the last one is the natural active credit. So all these methods can go to leads to the stochastic gradient descent algorithms. And for credit sites, we use different policy evaluation method that combined with the policy gradient. And this is the state of, there's some other recent papers that not yet covered. And most important one is actually the trust region policy optimization and proximal policy optimization. We might find another time to prepare for this presentation, and it's actually have many applications from the TRPO and PPO. For example, for the OpenAI's DOTA or their learning, their robotics application, they're all using things from PPO. They're using PPO as their baseline algorithms. And also more recently, there is some maximal entropy objective that combined with reinforcement learning that derivative to soft active credit. And this is maybe someone on me to present later. And this is the reference. And so I can get more understanding for the last natural policy gradient, and that's all.
Is Jim still online? Jim Dai?
Yes, not.
Is no longer online. Okay, so thank you very much, Yinru, for the nice presentation. I think we benefited quite a bit. In future, I think for our presentations, should be more, maybe emphasizing more on detail, on insights,
Okay.
on actual understanding. When you present an important piece of information, like a theorem or a key part, key insights, some brief derivation will be very useful.
Okay.
And contrasting with the previous approaches or what we already know, and to help us understand this better.
Okay.
I think that's my general comment. Otherwise, especially the first part of the presentation, it's clear, and then if not for couple of places where details are missing, would it be nice to have those details presented or included in the presentation.
Okay. Thanks.
Yeah, thanks, Inru. Are there other questions or comments from the audience? Well, I guess no. So thank you very much, Inru and Mark, and everybody else staying online. So thanks again.
Okay. Okay.
Okay. Okay. Bye-bye.
Bye.
小泉说是
那个人是谁？